It's you! Finally! Welcome back from I don't know, vacation, whatever. But you're here! My favorite pre-calculus student. Thanks for joining me. I've been waiting to see you all week. I've been thinking about, okay, we just finished up with conic sections. Now we've got to get into exponents and logarithmic functions. A little bit of a reprise from last year, talking about properties, talking about functions, graphing, but we're going to be getting more into applications along the way. But I'm super excited that you're here. Today we're going to talk about properties of exponents and properties of logarithms as a little bit of a reminder from what you had from previous experience. And as the week goes on, we're going to get into solving equations, the definitions of logarithms, and then quick reprise of graphing, and then a lot of word problems, applications, all those things that you need for calculus next year. Thanks for joining us. I was always thinking pre-calc, my favorite student, and here you are. So nice to see you again. Welcome back. Let's get started. Here we've got, we're going to go through our properties of exponents, look at definitions and some quick examples so that we see what we've got along. Make certain that we go, then we can figure out the practice up on Google Classroom today. So properties of exponents, I'm not going to go through the proofs. You've seen this in past experience. We'll define, give an example of each case along the way. All right, so first property of exponents we have is what we call the property of powers. When we are multiplying the same base, we can combine those into a single term by adding the exponents. Well, we've got a, many of these, a, many of b, many of these being multiplied. Together we have a plus b, many. So for example, if we have 2 to the 4 times 2 to the 6, together we have 2 to the 10. So product of powers. Next, if we turn that around, we have the power of a product. If we have a product raised to a power, this is the distributive property. This is not your FOIL, as you might call it, because that is addition or subtraction. When we are multiplied in the parentheses, then we can distribute the exponent onto each individual piece. We would have a to the n times b to the n. If we have 2x cubed, this would give us 2 cubed times x cubed, giving us 8x cubed. Next up, we've got the power of a power. An exponent raised to an exponent, we can combine those by multiplying the exponents. If we have x squared to the 4th power, that is going to get us x to the 2 times 4, giving us x to the 8th power. The opposite of multiplication, we have division. So the quotient of powers. Well, if adding, when we are multiplying the same base, when we add the exponents when we multiply the same base. So we're going to do the opposite. When we divide the same base, we would subtract the exponents. This would be the numerator exponent subtract the denominator exponent. That would be a minus b. So if we have x to the 4th over x squared, we would have x to the 4 minus 2 is 2. Subtract the exponents. Seeing the similarities, we've gone through the power of a product. Now we have the power of a quotient. We have the distributive property over division. We'd have a to the n divided by b to the n. So how if we have 2/3 to the 4th power, that would give us 2 to the 4th over 3 to the 4th, giving us 16 over 81. Negative exponent falls out of that subtraction. A negative exponent, well, that's like 0 minus a. So it would be like x to the 0 over x to the a. Thinking 0 exponent, we know that. But the negative exponent is the reciprocal. If we have some base raised to the negative exponent, we have 1 over x to the a, the positive a. That's the reciprocal. If we have 1 over x to the negative a, that would give us x to the positive a. Notice the reciprocal. Oh, if we have 2 to the negative 3, as an example, that's going to give us 1 over 2 cubed, giving us 1 over 8. We have 1 over 3 to the negative 2. That is going to be the same as 3 to the positive 2, giving us 9. 0 exponents, anything to the 0 power is always 1. Think about that. We can prove that easily by the quotient property, the power quotient of powers. We would subtract the exponents. We'd have something subtracted itself. So like 2 cubed over 2 cubed. 3 minus 3 would give us 0, giving us obviously 1 because we're dividing the same thing by itself. So anything, provided that x is not equal to 0 itself, is always equal to 1. 18 to the 0 power, doesn't matter, 1. And lastly, that we've got for our properties of exponents, our rational exponent. If we have the rational exponent, this is equivalent if we have the root. Oops, rewrite that. So a rational exponent represents a power and a root at the same time. So the bth root to the 8th exponent. So if we have 5 to the 2/3, we could rewrite this as the cubed root of 5 squared. We've got properties of exponents. On the other side, properties of logarithms. Logarithms are the exact same as exponents. Now we're going to go more into the definition of logarithms later on in the week, but here we are just going to expand or condense logarithms using the different properties that we have. Product rule for logarithms: if we have a log of a product inside, we can separate this. That is the log of the first term plus log of the second term inside the argument. So we can expand. Expand is when we go from an argument, some product, quotient, power inside our logarithm to some addition, multiplication outside. So this statement has been expanded to here. We might say condense. When we are condensing a statement, we are working backwards. If we have the sum of two logarithms, we can combine those into a single log by multiplying the arguments, the values inside. Opposite of multiplication: if multiplication inside gives us addition outside, the opposite of multiplication is division. Division inside would give us the opposite outside. That would be subtraction of the arguments. Log A subtract log B. So expanding, we would start with a single statement. We would end up with two statements. Condensing, going the opposite direction, we would combine into one. The last property of logarithms that we're going to have is known as the power rule. It's kind of a repeat product rule. But if we have an exponent inside, this is the same as that exponent coming out, turning it into multiplication. The exponent multiplied by log A. This works for any base logarithm, so we're going to get more into that as the week progresses, but we have those three properties of logarithms at this point. Expanding, we started with a single statement. We've taken the exponent out. Condensing, we would start with the product, rewriting it as a single logarithm going the other direction. Try out the practice on Google Classroom, and we'll pick it up tomorrow.